Let's go ahead and continue on to the last chapter for this term, all about aromatic compounds. So does anybody know the older definition of aromatic compounds? Oh, even older than that. Think about just the generic usage of the word aromatic in English. Smelly, right? If you call somebody aromatic, that's normally not a compliment, right? So the old definition for aromatic compounds was something that was smelly. It wasn't the best definition that we could come up with, right? So today we actually have a much more refined definition. So let's really quickly list the modern definition. All right, the modern definition actually has 4 different points that we need to keep track of. So it must have all of the following. Number 1, in order to be aromatic, it must be cyclic, meaning it must be a ring system. Number 2 is all atoms in the ring system must have p orbitals that are aligned. Another way of thinking about that is the entire cyclic ring system that we're describing in part 1 must be conjugated, which is what we talked about before, right? So we must have alternating double single bonds around the whole system, or we must have p orbitals that are aligned. All right. Number 3 is it must be planar, meaning the ring must be able to lay flat. There are a variety of ring systems that will actually twist and contort so that they're not planar, and we'll look at a few examples of those. But in order to be aromatic, we have to be looking at planar molecules. And then the last one's actually related to a topic we'll talk about next week called Huckel's rule, but it says that we must have 4n plus 2 pi electrons in the ring system. So then the question is, well, what the heck do they mean by 4n plus 2? N in this case is going to be a whole number. All right, so would 4 satisfy the 4n plus 2 rule? Would it? Is there a whole number n that you can plug in where this would spit out the number 4? No. What about 6? Yeah, you could get 6 if n equals 1. All right, what about 8? No. What about 10? Yeah, definitely. So really, this is just a quick and simple formula to use to predict whether or not a molecule is aromatic. So you can see we've come pretty far from the old definition of just smelly molecules to defining molecules that must meet all 4 of these criteria to be considered aromatic. All right, so like I said, we'll jump into this a lot more. There's a lot of nuance with predicting whether or not a molecule is aromatic or not, but we'll practice it a fair amount. But before we do that, I want to jump into nomenclature. All right, the nomenclature for aromatic molecules gets a bit more complicated. So if we think about a simple aromatic system, you might have a substituent coming off of an aromatic ring. So this is just referred to as mono-substituted. All right, but as many of you saw in the NMR chapter, we might have di-substituted systems. So for example, maybe we've got R, and then I'll call this one R prime, meaning a different R group. This is di-substituted, right? 2 substituents coming off the ring. We could have di-substitution where maybe the R groups are staggered further apart. Or maybe we could have a system that looks like this. All of these are di-substituted, right? In fact, I'm going to move this down. All right, so if we're talking with somebody about molecules that are di-substituted, we need to be really specific, right? Because we might be referring to different types of constitutional isomers. Does anybody know how we might be able to differentiate these using Iu Pac rules?
1, 2.
Yeah, 1, 2 or 1, 4. So for example, if we look at this one, we could say, all right, we could say this is 1, 2 disubstituted. We could say, well, this is 1, 3 disubstituted. Or we could say, maybe this is 1, 4 disubstituted. So sometimes you do see this. This is Iu Pac allowed, and it is a good way of describing the regiochemistry of these two substituents. Yeah?
What about if like R's are different, like bromine and chlorine? How can we specifically show which one?
Yeah, so that's a good question. The question was, what if the R groups are different, like bromine and chlorine? Well, according to the Iu Pac rules, which one do you think would be put at carbon number 1? Why bromine over chlorine? It's lower in the alphabet. So then we would still follow those Iu Pac alphabetization rules where the lowest alphabetical substituent would be placed at priority 1. Yep. All right. There is also a different way of describing these that's actually quite popular. So I wanted to show that. This is called ortho. And oftentimes people just abbreviate it as O. Ortho substitution is completely synonymous with 1, 2 disubstitution. The next one is called meta substituted. Again, you can abbreviate that as M. That's the exact same thing as something that's 1, 3 disubstituted. And then 1, 4 disubstituted is referred to as para, also known as P. So we can use these alternate Iu Pac allowed naming conventions to basically indicate really quickly the substitution pattern for disubstituted aromatic rings. Students will often ask, well, what about tri-substituted aromatic rings? What do you think we do then? Then we do the Iu Pac rules, kind of like I was doing with the red numbering system. Unfortunately, there's no quick shorthand system like ortho, meta, and para for tri-substituted or above ring systems. So we just stick with the Iu Pac system. All right, so let's take a look at some common Iu Pac names. So like I said, Iu Pac is the International Union of Pure and Applied Chemistry. They basically got chemists from all around the world together and said, this is getting crazy. We don't need chemists in Japan naming molecules different than somebody in England, than somebody in the United States, than somebody in Sweden, right? We've got to come up with a unified naming system. However, a lot of these old school names have just stuck around because people don't like change, right? So let's go over some of the names that are still sticking around because people don't like change. And luckily, Iu Pac actually even threw in the towel and they're like, fine, we give up. You can have some of these old names as a part of the naming convention. All right, so let's take a look at a simple one. What do you think Iu Pac wanted us to name this molecule? Just looking at it. Benzene is the parent, right? What's coming off as a substituent? Methylbenzene. However, most chemists would look at you a little cockeyed if you called this methylbenzene. Most chemists, since the 1860s, call this toluene. Don't ask me why, but that name has stuck around forever and people don't like changing it to methylbenzene. So toluene is usually the preferred name by most chemists. However, if you call something methylbenzene, people will still know what you're talking about. Either way, I want you to be able to understand what somebody means when they say toluene to you. So understand both of these names. All right, let's do another one. So again, benzene is going to be the parent. And then we've got an alcohol substituent. When alcohol is a substituent, it's called a hydroxy group. So you could call this hydroxybenzene. All right, but again, most chemists wouldn't call this hydroxybenzene. Most chemists would prefer to call this phenol. So both of these are Iu Pac allowed. Let's do another one. What do you think Iu Pac wants us to name this ether? I would say methoxybenzene. Some people would say methylphenyl ether, but methoxybenzene is probably a little easier to explain to somebody. However, most chemists don't call this methoxybenzene. Instead, they call this anisole. So that's usually the preferred name for that molecule. All right, let's do a handful of others. This next one has a carboxylic acid coming off of it. This is called benzoic acid. It's a really common parent group. It's also a common molecule. It's found in a handful of commercial products. We have the analog where instead of a carboxylic acid, we have a methyl ketone. This is called acetophenone. I still remember one year I had a student that kept on pronouncing this acetophenone. That made me laugh. It sounds very Italian when you say it that way. Acetophenone. No, it's just acetophenone. All right, and then the next one, we've got this group coming off like an alkene. It's called a vinyl group. This is usually just called styrene as the parent. Does anybody know what this is used in? Polystyrene, so it's a monomer for polystyrene. There's a few others we should hit. This is benzaldehyde. Another common parent. There's also one where you have an NH2 or an amine coming off. This is called aniline. It's a common reagent in organic chemistry. Students oftentimes get anisole and aniline mixed up, so make sure that you're really comfortable distinguishing between those two because it's an easy mix-up with the naming conventions. All right, and then the next one is where we have two methyl groups. So you could call this 1,4-dimethylbenzene, but most people don't call it that. They call it xylene. And to indicate that the methyl groups are off of opposite sides, what do you think we could include as a prefix? Para. So we can just write p-xylene or para-xylene. That indicates that the methyl groups are in that 1,4 disubstitution pattern. Does that make sense? All right. So these are really the main ones I want you to know in this course. So what I'm going to do is make a note here and say this, or these, I should say, are common parents in naming. And I'll show you a few examples of how we can work through naming aromatic molecules using some of these parent names. All right, so let's do a few fun ones. Let's do this molecule right here. All right, what do you think the parent is going to be in this molecule? Do you see a parent that might fit in? Methylbenzene, but most of the time we call that toluene, right? So what I'm going to do is I'm just going to highlight the parent in red, and I'm going to say, all right, this red highlighted system is my parent. Agreed? So that's toluene. And then I would want to number my other substituents. Where do you think I would start numbering 1 at? At the methyl. So we always start numbering at the priority for the parent. So that's going to be priority 1. In this case, it doesn't matter if we number going right or left because it's going to be equivalent. So we'd say 1, 2, 3, 4, 5, 6. So let's go ahead and try to name this. Well, we have more than 2 substituents, so we can't use orthoparameta. We've got to use the traditional naming system. So we could say, all right, off of position 2, 4, and 6, we have nitro groups. So what should I say? Trinitro. All right, and then the parent we said is toluene. So this would be 2,4,6 trinitrotoluene. Does anybody know what this is commonly referred to as? TNT. It makes sense, right? So we got TNT right there. I always thought it was funny too. If you watched my video last year, you already caught this joke. But the AC/DC song where they say, I'm TNT, I'm dynamite. Dynamite is not TNT. They were completely wrong. Dynamite is nitroglycerin that's mixed in with diatomaceous earth. It is not TNT, so they should have taken their chemistry classes. All right, anyways, let's go to the next one. Let's see if we can go ahead and name this molecule. And then check with your neighbor and see if you feel comfortable getting the name. All right, so let's see thumbs. Who thinks they got it? All right, so what's the parent going to be for this one? Styrene. So I'll go ahead and highlight it. I like highlighting my parent just to keep track of everything. And like we said, we always number 1 for the substituent where the parent's substituted, right? All right, should I go clockwise or counterclockwise? Clockwise. That way I minimize my numbering system. All right, so I've got bromine off of position 2, chlorine coming off of position 4. Which one should be named first? Bromine. So I go ahead and I write 2 bromo, 4 chloro, styrene. All right, let's do one more. This one might be a little bit different. What do you think the parent's going to be for this one? So toluene has to have a methyl group. We've got an ethyl group coming off. Do we see a parent in that special list? No, I don't think so. So what would our parent be if we don't identify anything in the special list? Benzene. So I just say, all right, we can't find a parent out of that list, so that means we're just going to default to benzene being our parent. All right, what's going to be position 1, the bromine or the ethyl group, and why? Bromine, why? It's lower in the alphabet, right? Okay, so we could go ahead and we could name this 1 bromo, 2 ethyl benzene. That would be appropriate. Or what's another way we can name this? Does anybody have an idea? What if we don't want to use the numbering system because this is disubstituted? Ortho. So we could say ortho bromo ethyl. It's implied that they're 1,2 disubstituted benzene. These are completely allowed, so you're allowed to use them interchangeably, but I want you to be able to interpret going back and forth. Yep. What if you have two methyls? What do you? So you're saying, what if we had a methyl group there? Oh, so if we had one there and one at the 5, it would be named something completely different. We would have to go through and work that as an example, though. Let me keep this in here so we don't get too lost. Yep.
So if we had something like a xylene
Mm-hmm.
with the 2 methyls, like you were saying, would we still, if there was like 2 methyls and something else, can we still use the P or the M or the O?
That's a good question. So xylene's kind of unique. Normally xylene, if it's substituted, we just default to using benzene as the parent because things are getting so complicated then. Really, you're never wrong if you use benzene as the parent. The reason I like showing these is just because they're so commonly used interchangeably that we need to know how to interpret both ways, the old school way and then the newer Iu Pac system. Good questions. All right. So then the question is, well, why the heck are these aromatic molecules so special? So let's make a little note. Whoops, like benzene. So special. It was really interesting when they started studying benzene. They knew benzene was unique, they just didn't quite understand what in the heck was going on with benzene that made it unique. So I'll show you a few ways that we can compare and contrast benzene. So for example, if you take this molecule and you treat it with Br2, so if you try to react benzene with just elemental bromine and nothing else, you get no reaction. However, when you do the same reaction with cyclohexene, you'll get addition of 2 bromine atoms. And you'll end up with a mixture of enantiomers. Why do you think this is the case? Resonance? So why do you think resonance plays a big role? Yeah, when we think about these bonds right here, are they really alkenes? No. They're a bond order of 1.5. Therefore, they do not do typical addition reactions. So that was one observation that they had. It was kind of confusing. They didn't quite understand, well, how can something be between a bond order of 1 and 2? And it wasn't until resonance theory came along that they started feeling more comfortable explaining that, hey, it doesn't have to be 1 or 2, it can actually be between. All right? Then they also had this really strange observation. All right? And this strange observation was doing similar reactions where they said, all right, well, what if we want to convert cyclohexene to cyclohexane? We can do that using hydrogen and palladium on carbon, and we can actually measure the energy or enthalpy of this reaction. And when they did this, they found that experimentally it was a negative 120 kilojoules of energy per mole of starting material. So they're able to measure the enthalpy of the system, meaning the heat being released or absorbed, right? So that's kind of neat. It's an exothermic reaction. Let's take benzene. And they said, well, either way, let's imagine that we hit this with a huge amount of hydrogen, 3 equivalents, and a special nickel catalyst, and we have to run this at high pressure because we know aromatic molecules are unique, but you can actually reduce benzene. All right, what would you expect the delta H for this reaction to be based on the observation above? Yeah, it was expected to be negative 360 kilojoules per mole. However, they actually found that the delta H for this reaction, the enthalpy, was negative 208 kilojoules per mole. That means when they were studying this reaction, they realized that there is approximately 152 kilojoules per mole of aromatic stabilization. It wasn't really well understood how this stabilization played into the orbital theory behind this, but what we'll do is next week when we come back, we'll start looking at why molecular orbital theory explains some of this unusual stabilization energy behind benzene, but that's where we'll kind of stop today. All right, there's no new pod tomorrow, but what I would encourage you to do is to start studying ahead for your finals, because I know finals week gets really busy, and this term we covered a huge amount of material, so make sure you start studying early for your finals.